Yes, hello. Greg Latch here from Emission Process Management. I'd like to say thank you for your attendance this afternoon. The session today is really talking about SEMS measurement, the extraction, sample handling, and then the technology that we have downstream for that, for optimizing, as I say, combustion measurements. The key points as we'll go through hopefully will be highlighted. If there are any Q&As, please let me know or contact myself via the LinkedIn process. So again, thanks for everybody's attendance, and yeah, look forward to your feedback. I'll just hold this slide up there for a little bit and let you guys absorb that, because I think there's a fair bit of volume in that. The first point, obviously, but also more so from an improvement of process in that second point. As I say, it's the bottom line is my thoughts for our industry today to stay competitive. Obviously, incremental improvements really help. So the thought for today, I suppose, is, guys, what sort of value does this add up to you and your plant if you don't consider, for example, process improvements for these sort of styles of plant strategy? The agenda, just briefly, we'll be looking at some of the considerations and challenges for SEMS, just as a really brief element. Some of the different sample systems and styles of monitoring, for example, extraction more to the point. A little bit of traditional and some of the monitoring technologies that have been used in the past and we still have currently available today. Then hot wet solution, which is a current application we're working with a client on at the moment, which is quite exciting. We'll talk about the technology itself, speed of response and how it can apply to process control, and I suppose then the summary and Q&A. This is currently a pre-recorded session, so I've got some previous Q&As that we'll also discuss post-session. So moving straight into it. Obviously, some of the challenges, as you can see here, for example, is really, hey, what do we need? What do we need from a SEMS output? What sort of reporting is required? And that's typically liaised with your EPA and or your emissions compliance aspects. So every plant's different, as I say. You've got various and varied processes, and really depends on what sort of emission you're looking at. Sometimes it could be anything as basic as, for example, a coal-fired boiler through to a could be a gas-fired genset, reciprocating engine. Hey, sky's the limit, as you know. Your applications are very wide and varied, guys. So some of these measurements and parameters that we have to look at do vary in its application to application. Probably one of the unnoticed aspects is definitely the size of stack and access to it, and some of the various risks and hazards that do apply to that space. And I won't dwell on that too much, but really I'd like to make a comment is you do have to really look at your OH&S requirements in that space as well. Type of samples extraction, unfortunately, as you're very well aware, 9 times out of 10, usually it's a very low pressure, unfortunately, and very often the case, very high temperature. Presence of water in the sample, obviously that's just a point of from combustion aspect. Is 9 times out of 10 there's obviously latent water as a presence from the combustion process. Ideally, you don't have SO3 from a process automation aspect and sample handling systems right through to analyzers. Yeah, that's not really friendly to have. Dare I say, very gooey and painful. Can be removed, but it's a bit of a sample handling challenge. Some of the technology selections for analysis. Again, it really depends on the application and what sort of resolution. High levels down to low levels you'll be looking at. We'll briefly touch on that as well. But more to the point also then from a representative point of view of what you're putting through to your regulatory authorities from a reporting analysis, daily, weekly, monthly, and hopefully not any excursions, and then the rectifications, actions and requirements, non-conformance, so to speak, for any excursions you may have on your plant. And dare I say, if there's any measurement corrections, typically done at the DCS stage or your control strategy. So in summary, those 2 bullet points at the bottom in the blue section, I think really, can my sample data be used for plant operation as well as reporting? My answer is yes, absolutely. These are some of the points we'll look at. So the challenges today, we've sort of touched on that previous slide on probably a fair portion of this. But just for those that aren't aware, this is just a little bit of a brief example of some of the particulates or components of interest that are measured in a combustion cycle. Obviously the CO2, everybody knows that is the commonly known greenhouse effect. CO, and as it says there, it's due to incomplete combustion. Moisture or water in this particular case, obviously direct, again, steam is never a pollutant, as they say. Traditionally, being an old school guy in the industry for some 30 plus years, as I say, everybody likes white smoke, as they say, coming out of a chimney, but not black smoke. So yeah, there used to be some interesting methods used at plants over the years for steam injection, also on the exhaust area. Obviously N2 and all the components of that. It could be NO, for example, as an inferred value of NOx through converters, for example, NOx converters, SOx, SO2 or other, and SO3, which is a horrible one. O2, obviously, we want to have, if we can, a very low O2 level as we can, so you do end up optimizing your process fuel as much as you can. DNOx, for example, depending on your application, you may have that process, depending on what you're up to with regards to denitrification, so to speak. And H2S, obviously, depending on your fuel source. Coal, for example, typically it does have sulfurs, depending on your gas and or even your potential liquid fuel, you may have sulfurs. Hopefully, from a process point of view, you don't have HCl and HF, but definitely common in the process industries today. We can manage those processes as well. I'll touch base on that later on. Obviously, they become quite problematic in a liquid form. And obviously, particulate matter. The main aspect of that is obviously you don't want to carry any junk, as they say, through your process lines, more to the point into your analyzer ideally. So if you can, as I say, stop that at the pass, at the point of extraction is ideal. So typical combustion streams and compositions, I think we've pretty much touched on that with regard to the points of measurement. This is just a traditional everyday style of combustion stream. Example, some of the limits and the likes. I sort of alluded before with regard to acid dew point concentration or consideration, so to speak, and we'll also touch on that and the styles of measurement extraction you can have. But I suppose in summary, depending on your application and what your challenges are, from the SEMS point of view right through to even combustion control and maximising those efficiencies, we basically engineer your sample handling to suit and obviously the downstream technology for measurement of those components of interest. And probably the last summary in that particular slide, and based on the previous, as I say, based on application, you're only as good as your sampling. Okay, some of the designs used in SEMS, for example, we do, I have seen and obviously worked with, for example, extractive cold dry. As I said, there's different approaches to achieve this. We'll touch base on that through the next few slides. The upside for this actually does minimise the use of electrically heat trace lines coming down off the stack. Okay. There's maintenance of the sample system at the takeoff point, because what you are doing is removing any liquids up at that potentially OH&S risk point. But in saying that, obviously you can in process and procedures to manage that risk for staff and personnel up at those heights. Typically they're at heights. Okay. High ambient temperatures of the stack due to radiant heat, not uncommon. For example, some of the industries I've dealt with over the years, geez, you can have stack emissions temperatures up in the high 600s to 900s, depending on what your application is. I see that a little bit criminal, just to make comment with regard to that waste and latent heat, that you could use that for cogen, for example. So these are the areas to consider for future optimising your plant. Extractive hot wet, heated lines in accordance to acid dew point issues, if there are any. So again, extractive hot wet is, again, managing the sample from the takeoff point from a particulates point of view, elevated temperature, all the way down through to either locally close coupled analyzers at the takeoff point, or typically off and to safe areas down on ground levels or better access points at the analyzers in their own right. Typically there's water removed in the traditional hot wet formats, by, as we say, mechanical coolers and dryers. And there's other options depending on your application as well, as we spoke of. We won't delve into it too great, but depending on if you have very high, for example, nasties, to use that terminology, and or excuse me, sample turndowns, for example, what we can do is do dilution probes and the likes, to, dare I say it, scrub off or dilute the sample coming through to the analysis system. Just a little brief example of some of the sample takeoff points you can have. Point one, hopefully that picture comes through relatively clear, but you've got level 1, 2, 3, 4, and 5 there, for example. So depending on the measurement parameters that you're physically looking at, this is just some examples with regards to an EN 1481 guideline for EPA takeoff points. Obviously, gas sample probes or your sample point, your gas extraction. Particulate meters for sampling for the sample probes as well. Can be typically it's a separate system in its own right. Isokinetic sampling points. Typically that's used the word homogeneous, so to speak. Opacity, if required. Again, sometimes that falls into the realm of the particular particle load meter, for example. And all of these aspects do come into play, again, depending on your EPA licensing. And or even your own requirement from process control optimizing this. Okay, and not to be obviously forgotten, from an EPA exhausting aspect or release, you do need to know your stack flow rates. You can use things like annubars, for example, using multivariable flow meters for compensation with pressure and temperature. And that detail is very handy, obviously, to have to give you your load mass balancing as well for your plant. Not to mention then to time and date stamp your rate of emission and what sort of excursions you may have had at any particular moment. Some of the sample probes that we use, we'll be generally talking about heated sample probes in these in this session today. Some of those are just really just quick snapshots just so you have an appreciation of what they look like. Some of the aspects though you do need to actually understand is obviously the zoning of the area. Not always a zoned area, bearing in mind it's actually it's an exhaust point, can be elevated temperatures. Some of the applications that I've come across can be, for example, zone 1, zone 2. These have to be obviously acknowledged and dealt with accordingly. Mounting access for the maintenance of these particular styles of probes, excuse me. And obviously the materials of construction, as I Google, excuse me. Some of these materials of construction, as we suggested, if you've got, for example, HF acid, for example, as carryover, HCl, etc., potential emissions, or even heavy loading particulates, you do have to very much look at the best wetted, or if you like, call it exposed materials of construction. And then that follows through to things like blowback, for example. We've got blowback scenarios, and more importantly, definitely from a SEMS point of view, you've got calibration re-entry point. So you actually re-enter your calibration gas at the point of takeoff. And the methodology for that is you're proving and testing the full function of the measurement system. So there's no shortcuts there from a SEMS aspect. For process control, it can differ slightly. Sample systems, just to give you a little brief overlook on traditional, what we call cold, dry system. As we discussed before, you've got your preload sample takeoff point. Ideally, you've probably taken out the majority of your particulates and the likes at an elevated temperature. Close coupled to that, then you have, in this particular case, we're just showing a pump and we call a heat exchanger, just an air heat exchanger in this particular case. Obviously, some of the challenges in that is depending on your air temperature and open to a hot environment. And again, being close coupled to, dare I say, the point of extraction, you do get a lot of ambient and latent heat, and that can and does affect your efficiency of that heat exchanger. Going down through the system, then obviously you're now heading off to a kinetic separator in this particular application, going down for all your liquids. And then off up to the far right, you're going through a particulate, the final point of let's call it filtering before your standard analysis system. You've got just, for example, like a Genie filter or particulate catching device in your sample handling. Obviously, you do have to be very aware, for example, obviously with the aspects of liquids in your process streams, and then in saying that you will have potential knockout of some of those components of interest from a dew point of view. So the graph there just represents, for example, sulfur dioxide solubility in water. And obviously we're knocking out water, so you do have to be aware of that. The sample system here that we're just showing is just further down the stream and specifics on a kinetic separator. As you can see, the one on the left, for example, is actually what we call a traditional unit based on some ambient air. The one on the right has items like, for example, a vortex cooler embedded in the head and the likes. The upside for that is it does give you a better cooling effect on the application and the measurement or the gas stream. There are other technologies available, for example, things like a Neptune dryer and the likes. I absolutely love that technology. The PermaPure membrane, for example, works on, as they say, relative vapor pressure to purge and dry the sample. The comment I can add to that, though, is you're only as good as your dry air purge. So if you've actually got a very poor air supply, the efficiency of that PermaPure membrane technology is not, as I say, up to scratch. Therefore, you will get carryover. And that is a very big challenge then for your downstream sample handling systems. And then from there, you can have challenges with your analyzer. So the goal is moisture removal, obviously, in a cold dry aspect, moisture removal prior to the sample gas before transport of the analyzers, and or therefore some management of dryers just before the analysis. If you don't have that, then you will then have, dare I say, maintenance issues ongoing with your analysis system, and more to the point, dare I say, some potential large bills on your gas analyzers themselves. They don't like liquids going through them. Okay, I think I've covered a quick mention too, these sort of styles of systems though aren't always very suitable for DNOx. As I say, in this particular case too, I just had a note for myself that Neptune dryers, for example, don't work very well with ammonia, unfortunately. So it's one of the challenges in that space. Hot wet, this is a little bit of a brief overview, and hopefully it looks fairly clear again coming through as we're moving through the slide deck. Hot wet is a traditional SEMS aspect as well. In this particular case, what we're doing is having the sample handling system and the analysis down typically away from stack and the high temperatures, and also the hazardous from our HNS point of view, general maintenance and the likes. So we're having a heated elevated sample probe, takeoff point, elevated sample transport, and obviously removing all the particulates ideally at the point of takeoff. Obviously then we'd go back and calibration injection at that point as well of the stack. And going from left to right, we've got off stack, typically down at ground level or a mezzanine floor. You'll have your sample handling and conditioning system, which will then be coolers and dryers. And you can see pumps, for example, easy access for ongoing support and maintenance at local level. And then to the right, as you go through, for example, you've got, in this particular case, we're showing a NOx converter, for example, and then all your different benches in a traditional gas analyzer system. Yeah, sometimes they're multiple or individual analyzers. 9 times out of 10, that's typically the function and how they're set up. But as we know, you've got anything from IR, UV, etc., depending on your components of interest that you're physically measuring and looking at. And then, as you can see, then you've got your suite of calibration gases. And as you can follow that line back up, you can see it goes back through this point of entry as the takeoff point. Just making sure I've covered most step points again. And again, some of the downsides for this particular application in this case is obviously ensuring that you don't have any wets and carry over, and your sample handling system is up to speed in this particular case. Some of the downsides, just as a brief summary, as an overview for both of those systems, every time obviously you start placing components that manage your sample handling stream within the loop, you do tend to have what we call an RC network, R being restrictive, C being capacitive. So obviously now increasing your capacitive and your restrictive processes from a sample through an analysis system, your analyzers. and this will potentially create some challenges in timing. And from a process control point of view, time is your enemy. Ideally, you do want to have a very fast update time. You can manage some of those aspects, and that's through what we call fast loop processes, which we don't touch on today. But again, in the same context, you still do have to then manage that process from a wet point of view, managing those wets prior to analysis. So this now moving into the hot wet solution that we're looking at with a particular application today, and quite an exciting one. Same sort of functionality as we spoke of before with regards to the hot wet extraction. Sample a heated probe coming off the stack, any particulates obviously removed at the point of takeoff ideally straight away, and then downstream we manage any other particulates thereafter. In this particular case, as we look at the top left, got your heated sample probe. It's actually a heated trace line, so not dissimilar to the traditional what we call a hot wet system. Then going through into your sample handling system panel. Our sample handling system panel in this particular case is actually running at an elevated temperature as opposed to cool, which happens in a lot of the cases as well. So in this particular case, we're actually running this cabinet normally at around 160 degrees C. And then you can see that second arrow, we're now running through a particulate filter, just for any remaining loading, if there is any particulates or loading elements. And then from there, we're actually going straight into, in this case, what we call a quantum cascade laser analyzer. And this particular unit has an elevated cell temperature also at 160 degrees Celsius. So the subtle difference is on this is we're actually having a heated trace sample from point of takeoff all the way through the sample handling system without any liquid or moisture extraction, running everything at an elevated temperature above dew point, running it through the cell. We're compensating for anything that's within that cell because we do understand our gas composition, which we'll touch base on shortly thereafter. And then as you can see, we manage the pressure. Obviously, gas density and components of interest obviously have to be managed at a particular known pressure and temperature, hence the 160 degrees C. We go through a little RC network post measurement just to help assist any pulses that may happen in the system, for example, depending on the operation, and also the pump. And then from there we go through to a vent header. And all the liquids are then managed post-measurement, not before, which is a little bit different to what's traditionally happened. You can also see briefly that there is a little bit of a system there for a fast loop. So there's a pump downstream of what we call a header system there. Just showing you one loop. This particular application does have several loops, if you like to call it, or points of measurement, stack points. And the main design for this, I'm showing you the one point, is the fast speed response, which we'll talk about in a second. So just to give you some examples, running at 160 degrees C, the vacuum regulator actually has a vacuum. We're running a slight vacuum at the technology point, which is the cell, leaving it half an atmosphere. We spoke about the RC network, and based on the flow rates we can actually get through this system. This is over and above a fast loop system you may have on this on your takeoff point. We can actually run this analysis system at 5 litres a minute. So just to hopefully let that sit in and actually absorb that for a little bit. It's a very high and fast flow rate for a measurement cell, 5,000 cc's in a minute. And based on a 1/4 inch line, with a 40 metre sample run, we can look at an update time without a fast loop of under 8 seconds. So that's, I'm actually quite excited by that process, and making that comment of, yes, for example, SEMS measurements can be used definitely for process control. This gives you just a little brief overview of some of the components of interest on this one application in particular. It's not unusual in any way, shape or form. Obviously, we're now looking at NO and NO2 and N2O without any NOx conversion, which is a direct measurement, obviously, to calculate as opposed to calculating out NOx. CO, CO2, solid dioxide, O2, obviously we expect potential residual and carryover. Probably the strange one, everybody will be looking at it and go, geez, it's a hell of a lot of water. The application on this one in particular is for turbine efficiency. This particular turbine scenario for LNG compression is they do liquid injection, water injection. The application for that I won't go into any detail on, but that helps with efficiency of combustion. Probably not uncommon to a lot of people out there, but those that may not have heard about it, definitely hit the web. There's some very interesting articles in that space as well. From a technology point of view, we'll be talking about it shortly, but we don't measure what we call noble gases, things like argon, for example, and hydrogen and helium. So the technology we use is spectroscopy, and obviously from in that space we have challenges with what we call noble gases. I think I've covered most points in this. We're talking about the Cascade technology. Okay, just a little bit of a brief overview on the actual cell, or if you like to call it the analyzer in its own right. Obviously, we have what we call a QCL technology, which has a chirp technology embedded in the laser. We'll talk about that in a separate point. That's embedded, obviously, within the analyzer set. So, from a spectra point of view, it is spectroscopy we're using. We can actually tune, to use that terminology, or look at particular windows to optimize the actual, quote unquote, the components of interest. We'll also touch on that. The cell is what we call a Harriet cell, so it's what they call a multi-pass. So hopefully this works. So we've got multiple passes within the Harriet cell depending on the resolution. Traditionally, for example, if you've got a high range, the cell is very small, if you like to call it, with regards to its distance. If you're looking at a low resolution, for example, that tends to obviously become longer. So we can actually run a cell in a very small space due to its multi-pass technology, or we can actually go up to 30 meters, for example, in the multi-pass technology. And variations and options to suit on that. User interfaces, obviously with the technology we've got today and evolving through the Emission group, USAID's got all the bells and whistles you'd want to have. Anything from fibre optics directly coupled to it, through to obviously RS-232 if you wanted to do 485 wide technology, Modbus, etc., and RTU Cat5. Next. Okay, this talks a little bit about the technology and how there's a crossover between TDL and QCL. So QCL stands for what we call Quantum Cascade Laser, and TDL, which a lot of people are very familiar with, stands for what we call Quantum Cascade Laser, and TDL, which a lot of people are very familiar with, being tunable diode laser. They're similar but different. We'll talk about the subtle differences in a tick. But I suppose in summary, TDL works in the NIR space, and we work in the MIR, the mid-infrared. So if you look at the components of interest in those spaces, they do vary, and there's also crossover. We use both technologies in our Cascade systems, our measurement devices. So we actually optimize the application to suit, and we pick and match our laser technology within the actual analyzer. The technology works on what we call a beer and Lambert, and so I smirk about the beer aspect after lunch, so hey, it could be beer o'clock, but it's a beer and Lambert law. The main part about that I do like about it is, hey, it's based on the laws of physics. Nothing changes. There's no cheating. There's no change. Once, as they say, you bed down the first principles, we actually have algorithms embedded within the analyzer, as they say, calculate for linear and non-linear ranges, and we'll look at some of the linearity points that we've got further down in the slide deck as well. But again, if you do want to become an instant expert, definitely have a look at some of the points on our website, right through to even obviously the internet on the laws of physics for beer and Lambert for spectroscopy. QCL, how we differ from TDL. Okay, we have what we call a single electron, so I use the word we actually excite a structure, so to speak, from the laser structure, which produces what they call a photon at multiple steps, what we call a cascading, where it goes down through different wells, and each well, believe it or not, actually emits a photon. As we go down through these particular wells, we emit multiple photons, This is over a very small wavelength, so we're actually over a number of wave numbers. Some of the things that I do like about this is you do then end up with, my terminology I suppose, like a common mode rejection aspect. And so you do get multiple points to physically look at that component of interest. CDL is slightly different. Obviously we just look at, in this particular case, a single photon that's released based on electron relaxation in this particular case. So we do mix and match, again, our technologies depending on the application to optimize the measurement. Doping, we use doping technologies as well. So if you like to call it the benchmark, it's set the first principle aspect of the wavelength, and then over and above that we change in the QCL space the material thickness as well, and that really does assist, if you like to call it, the fine tuning of that wave number that we're looking at. Gives you a quick overview of the size. On the left there's a QCL unit. Something I didn't comment on, one of the reasons why you do get also a wavelength change in those multiple photon releases is because laser technology can be high powered. We actually use a high powered style of laser which has an embedded Peltier cooler. So based on a heat cool cycle you do get a slight frequency shift and change versus TDL, which is more of a lower power style of technology. But as you look at these main points, I think they pretty much explain themselves. Basically it works on first principles. More to the point though, it's a technology that's been out there for greater than 10 years, and it's been based off CDL technology originally. We do know it's proven and tested, and we do have quite a number of these installed out in the field already in multiple applications from SEMS. Here in Australia, right through to international applications, through to aerosol applications, right through to process control applications. We also encompass, depending on, again, the application, wave modulation spectroscopy, and that's also employed depending on the application and the measurement. Okay, just a really quick one, just to look at it. We touched on this before. For example, QCL and TDL work in the same space occasionally for the components of interest. And as you can see, there's a little bit of an overlap in the H2S spectrum. As I say, it absorbs in both of those wave lengths, wave regions. Okay, so depending again on the application, we may have a preference to use TDL or QCL. So we'll engineer that in the background depending on the application. Some key points there that works, for example, on the TDL. I'll let you guys read those points. Same again, we're looking at NO measurement in this particular case. Very strong. I think that obviously in this particular case, from a spectroscopy point of view, obviously it's a no-brainer. We'd be choosing QCL in this space. Again, it typically has a clearer and what we call a better image, to use that word, so to speak, in mid-IR. So obviously it's a clear contender and winner for NO. I just wanted to show that as an example. The chirp technology embedded within the analysis in its own right. I think I've probably explained a lot of that, but as you can see, the speed of response there, it's actually very, very rapid. My terminology, it is a little bit like a machine gun scenario. So we actually emit multiple photons. We look over a very small wavelength period, or multiple wave numbers. As you can see there, you're talking, for example, less than 1 millisecond between the chirps in their own right. You can see, for example, some of the resolution, some of the absorption that's carried over. So to give you a bit of a snapshot, rapid analysis, for example, up to 10 hertz. Okay, so that's a continuous cycle pulse measurement, and that's the key to our speedy response for our cascade analysis. Again, compared to traditional technologies, this gives you a little bit of a snapshot on the clarity and some of how we can look at different QCL points or wave numbers and optimize the measurement. We're physically looking for a component of interest, so depending on the wave number, and if you like to call it, to optimize the measurement to get what we call the best fit, which we'll talk on the next slide on, just so there's no use the word overlay or potential noise from any other components of interest there, compared to traditional technologies like IR, for example, in the non-dispersive, etc. Okay, spectral fittings. when we spoke of the fitting sides of things. In the background, back in our offices, we've got an asset that's probably about £500,000 sterling in our Scotland office. That generates a library through spectroscopy testing, and within that library we actually know how a particular species, a gas component species, works and operates under particular temperatures and pressures. And what we do, we actually fit that data set embedded within the Cascade measurement system. And as you can see there, there's some examples, for example, of nitrous oxide and methane, depending on the wave numbers. The red, for example, is the fit data, and the real data for the measurement. The difference that we use in this particular case, we actually look at the area under the graph, which is a little bit similar to GC technology, as opposed to wave height. So I think, and based on, if you look at multiple points of measurement as well, we do end up with a more accurate and less, as I say, cross interference in that space. Just a quick one, just shows you an example of a single analysis. We're using CO2 spectra there for on the top right-hand graph, and NO for blue. You can see, for example, we can pick up 2 points, 2 components of interest in the one laser scan. We can do multiples depending on the amount of lasers embedded within the analyzer in its own right as well. And then, for example, that bottom right-hand unit, if there is a gas or a background variation for something that we weren't told of or didn't account for, we can actually see that. And then there are certain engineer around that. So if there is a gotcha moment that might come into play, we can definitely manage around that and have done, quite easily done, believe it or not, as well. And it's based on the fingerprinting of our fitting program / algorithm. When we spoke of some of the elements of the linear region, if you look at some of those points in the graphs, it's quite astounding with regards to the R2s that we have there. You're talking 999 is your worst case scenario. You've got, we've actually got a 49 there, for example, in some of the applications as well. So I'm quite astounded with regards to the linear aspect of the measurements we can do through the fitting and the algorithms that we have embedded within this technology, which is absolutely crazy. So yeah, very proud of that fact and the technology we now have embedded within our system. As we're heading towards the end of the slide deck, Cascade, from a long-term stability point of view, as it says, works on the first principles of the Beer-Lambert law. Obviously, hey, nothing changes in that space unless the physics are going to change in the future, which I'm not very aware of. Obviously, it works on absorption, concentration, and path length. We manage all of those. Obviously, the path length doesn't change with time. They're fixed and firm. The absorption properties of the gas do not change, and we've got those fixed and firm. Obviously, management of pressure and temperature is also managed, believe it or not, within the cell and around it from the sample handling point of view. So we actually compensate for that live. And with regard to the inherent stable measurements, for example, that we do have in this technology, and baselines based on, as I say, linearity, etc. We're talking greater than 10 years in mean time between failures. So it's absolutely exciting times moving ahead in this gas analysis space. And in my terms, in my eyes, this gives great confidence, obviously, in the measurement and repeatability, depending on your application and your requirements. Just a really brief snapshot of, as a little bit of an extrapolation of the CT5400. So a comment I didn't make earlier on as well, with the hot-wet applications, we have 2 series that can cover that space. This particular series, for example, the CT5400, we can run at high elevated temperatures in the cell. We have a 5800 series, which is an EXD series that cannot run at elevated high temperatures. The reason for that being is it's in an EXD enclosure, and the T rating obviously on that would be limited. So EXD enclosure, we cannot run the cell at very high temperatures, so we have to limit the internal temperature of the system in that particular case. So therefore, we can't always do hot-wet, obviously, to keep things above dew point in an EXD enclosure. But we do have a Zone 2 solution in the CT5100 series. Hit our website, have a bit of a look at that, and also the SAFE series in the CT5400 series. Again, I think that PowerPoint pretty much is self-explanatory with regards to its basic. This is just a little bit of an example of some of the components of interest we can look at. Over and above that, we can cover a wider ranges of measurement, right through the limits of detection, depending on your application, and repeatability, which when you look at some of those points, plus or minus 1%, as I say, of the reading, or as I say, of your limit of detection, which is the greater. Just in that space in its own right, a very exciting technology. That last point talks about DNOx, for example, and some of the applications being developed continuously as well. So, yeah, again, have a chat to us. More than happy to take your applications on board. And as I say, we do enjoy your inquiries. Challenging, I tend to find a lot more enjoyable. Yeah, that's good fun. So I suppose just as a little bit of a summary as we're heading down into the last of it here, regards to hot, wet, speed of response for SEMS, absolutely, response is key if you do want to start to implement control strategies. Some of the applications I've had over the years can be very scary with regards to trying to implement control strategies, utilising feed forward, obviously, depending on load of plant. Feedback, obviously, is the space we're looking at in this particular case. There could be feed forward, for example, within the space of gas composition being fed into your combustion process. For example, could even be in a liquid space with specific gravity. And so there's, depending on your application, we can obviously help and assist holistically around your combustion process. And we have algorithms and a lot of technology from control strategies and Delta V, and obviously field components in that space that do measure those areas of, I suppose, key variables we do need to lock down. But in summary, hot wet measurement minimises sample handling system complexity, which I'm very excited about. Increases, I should say, decreases sample transit time, so we can do fast loop applications, but more to the point, increase that speed of sample going through the analysis measurement as well, which is new and exciting. And the other part with regard to the true hot wet measurement, actually you're no longer now scrubbing out components of interest, and they tend to happen, as I say. And it's, as I say, it is complemented with the QCL technology and the elevated cell. So QCL has fast measurement capabilities up to 10 Hertz, for example. So we're actually doing multiple points and components of interest, multiple gases. So it can fit up to, for example, in this particular case, 6 laser streams, mix of match of TDL and QCL within the analyzer system in its own right. And with, for example, up to 6 laser systems, we can do down multiple analytes up to 12. Depending again on your gas composition, you may only have a number of lasers in there, and you may do, for example, 3 to 4 analytes in the one analyzer. Repeatable and measurement technology. Hopefully, we've covered some of everybody's fears in that space. Stable and proven measurement technology based on TDL. QCL also has been out there for 20 plus years and been designed and developed with our good Japanese friends for a number of years, and we've embedded that technology in ours going forward. And QCL with a twist, as I say, is a patent technology we own and operate. Low cost of ownership due to its stability alone, and your calibration gases and your frequency and sample handling management. So I suppose as a little bit of a thought as we wind up, and apologies for running over time, how could you optimize your combustion process with a faster sample update time? I'll leave that thought with you. And obviously in saying that, then obviously with reduced on costs, ideally, and on costs from a calibration point of view and sample handling aspect. Just a couple of, another little point just to give you a bit of a snapshot in an application that we've done with a company called Rolls-Royce, optimizing what we call jet engines, or if you like to call gas turbines, which is what they are. We've done some R&D work with them, and believe it or not, we've given them 300 updates in a 30-second period, for example, based on this technology. And what they wanted to do is they had a starter on their gas engines, and their turbines in this particular case. They wanted to optimize and manage the first 30-second startup to optimize the efficiency and startup of that particular gas turbine. So based on that technology, fast loop extraction, and then obviously a very fast update time and the volume of sample running through our analysis system, we've got, for example, 300 updates in 30 seconds. So that's, in my eyes, wow, that's just game-changing. So that gives you a little bit of a snapshot of some of the applications we can and have done in the past. So I'd like to thank you very much all for your time. And if there's any other queries and questions, please let me know. There was a couple that were brought up in the session just recently. Can the lenses, or if you like to call it the mirror faces, be cleaned in the field? Yes is the answer. From a purist point of view, being an instrumentation guy of old, I'd probably have a preference to do that in a clean area, but based on what I've seen in the field and the guys I've also seen do it in the field, they have done it in the field. One of the other questions was, can it be used for fast process control and optimizing of combustion systems? Yes, I'd like to reiterate, this is a game-changing technology, and yeah, definitely faster in speed and response. So talk to speed your application. Speed, reliability, and stability is king. We'd like to think our cost of ownership is very minimal for calibration cycles, and single calibration point gases can be also available because of the fitting that we have within this technology and the gas compositions we can cover over that space. Again, thank you very much for your time and acknowledgement. Take care, look after yourselves, and if we can ever help you in the future, please feel free to contact myself and my colleagues. Bye for now.